Lipids are a class of compounds that generally have been found to be the most pleasing tasting molecules to people, or at least the most satisfying. Um, if you think about some of the food you like to eat, chances are part of the reason you like that food is because of the lipids that it contains. Basically, the feel in the mouth and just the general feeling of satisfaction over eating something is sometimes directly related to the lipids that it contains. And of those lipids, probably most of it deals with fatty acids and triacylglycerols that are present in the lipid. We'll talk a little bit about fatty acids and triacylglycerols, as those are actually the predominant form of lipid that we have in our diet. In addition to fatty acids and triacylglycerols, we also have waxes. I won't spend any time talking about waxes, but waxes basically are derived from, they're an ester that's derived from a fatty acid and a fatty alcohol. Fatty alcohols are basically long-chain alcohols. Phospholipids and sphingolipids are components of membranes, and we'll talk a little bit about the differences in their structures. And then finally, we'll talk about isoprenoids and steroids, looking at how we can make a completely different class of lipids and from that get molecules like cholesterol, which is a derivative of isoprenoids. And the last thing we'll talk about in this chapter will be membrane structure and function, as well as membrane transport. So fatty acids are the most predominant lipid that we find in our bodies, as well as the lipid content of the food we eat is predominantly derived from the fatty acids. Basically, a fatty acid is a long chain carboxylic acid. Usually there is an even number of carbons in the fatty acid. In general, most of the fatty acids that we encounter will have a minimum of about 12 carbons, and usually the maximum is somewhere around 22 or 24, although there are exceptions to this rule. There are obviously some fatty acids that are longer than 24 carbons. In general, most of the carbons that we deal with in our body are 16 and 18 carbon fatty acids. Fatty acids can be divided into two categories, the saturated and the unsaturated. Saturated simply means that every carbon, with the exception of the carboxylic acid, is saturated with hydrogen. So every carbon is going to have at least 2 hydrogens on it, except for the terminal carbon, which would have 3. In terms of unsaturated fatty acids, they have at least 1 carbon-carbon double bond. And you can have a monounsaturated fatty acid, which would have just 1 carbon-carbon double bond, or a polyunsaturated, as seen in the figure down here. Linolenic acid is a polyunsaturated fatty acid. And you'll notice that in the structure we have cis double bonds, and in nature, basically the most commonly occurring carbon-carbon double bond in a fatty acid would be a cis double bond. And we'll talk about how that can be changed a few slides from now. Now, you'll notice that next to the name of linolenic acid, I have this notation here of 18:3 delta 9 12 15. What these numbers mean is the first number, the 18, indicates how many carbons are present in the fatty acid. So in this case, linolenic acid would have 18 carbons. The second number indicates the number of double bonds. In this case, we have 3 carbon-carbon double bonds. We don't count this as one of our double bonds. And then the delta 9, 12, 15 refer to the positions of these double bonds. This would be carbon 9. So we start off here with carbon 1, and then here's carbon 9. Down here would be carbon 12, and then here would be carbon 15. You always do the number of the lowest number of the double bond. This would be carbon-carbon double bond across carbons 9 and 10, but we say the position of that is at carbon 9. So you can classify any fatty acid in this manner. For a saturated, basically you wouldn't have any of these numbers here, and then this number here would be a 0. For any of the other unsaturated, you can very easily draw the structure based upon the notation that is given. So saturated versus unsaturated fatty acids and how they influence these structures that form. Basically, a saturated fatty acid will pack very nicely against another saturated fatty acid. Notice that in these two fatty acids here, the R groups, or the alkyl chains, line up fairly nicely with each other and can actually pack into a fairly nice structure. However, if you throw in an unsaturated fatty acid, it doesn't pack very well because the cis double bond prevents that close packing. Whereas saturated fats can form these kind of nice rigid structures, unsaturated fats tend to have a lot of degree of freedom because of the kink in the alkyl groups of the fatty acid chain. Basically, this gives rise to the saturated fat and unsaturated fat in our diet. And as you hopefully know, saturated fats include things such as lard or butter. They tend to be solid at room temperature, whereas unsaturated fats largely consist of oils. Oils are liquid at room temperature, and basically this is the reason behind it, that saturated fats can pack very nicely and have a relatively high melting point, whereas the unsaturated fats do not pack together very nicely and thus tend to have fairly low melting points. So if you look at some of the fatty acids in foods, I've kind of broken it down into some of the most more commonly observed. Over here on the left, the lauric and myristic acids, these would be 12 and 14 carbon fatty acids respectively. So these are kind of your shorter chain fatty acids. Palmitic acid is a 16 carbon fatty acid. Stearic is an 18. And then over here in the green section we've got the unsaturated fatty acids. Oleic is an 18 carbon fatty acid with 1 double bond, and linoleic is an 18 carbon fatty acid with 2 double bonds. So if we look at some typical sources of fat in our diet, if we look at, for example, beef, people tend to eat a lot of beef. The predominant fats in beef are largely derived from the saturated fats, palmitic and stearic acids. Usually at least about 50% of the fat in beef will come from these sources. A fairly large portion is derived from oleic acid, which is a monounsaturated fatty acid. Beef generally gives rise to milk. Most of the milk that is consumed comes from cows, and thus it does contain a fairly large amount of palmitic acid. Mostly the stearic acid is largely eliminated. It does have a relatively high concentration of unsaturated fatty acids, basically since it is in a rather liquid form. If we look at some of the plant sources of fats, coconut is often derided as a relatively unhealthy fat because it contains a lot of saturated fat. About 74% of the fats come from these short chain fatty acids, lauric and myrcitic acid. However, this is a fact that is actually being debated mainly as a result of looking at diets that are relatively high in coconut and other plant products, finding that people are not quite as unhealthy as they would be thought to, as they're thought to be. There's actually a growing idea that maybe the shorter chain fatty acids, less than 16 carbons, tend to be fairly healthy. So there is that distinct possibility. In general, coconut doesn't contain a whole lot of the long chain fatty acids, the 16 carbon and greater, does have a small amount of unsaturated fat. Palm oil, which has gained a lot of notoriety lately, basically it's found in fairly high concentrations in Girl Scout cookies, for example. The bulk of the fat there comes from two sources, palmitic acid and oleic acid. So it does contain a monounsaturated fatty acid, but it does contain a fairly high concentration of saturated fatty acid. Corn oil, on the other hand, contains very little saturated fatty acids, generally less than 20% saturated fat. It's got a fairly high amount of oleic acid and a fairly high concentration of linoleic acid. Basically, depending upon when the corn is harvested, the amounts of oleic and linoleic will vary quite greatly. The one problem with corn oil, however, is that it contains a very high concentration of omega-6 fatty acids. And an omega-6 fatty acid is a fatty acid that has a carbon-carbon double bond that is 6 carbons away from the end of the molecule. So if it's an 18-carbon fatty acid, the carbon-carbon double bond would be 6 carbons away from the carbon 18. Omega-6 fatty acids have been shown to be relatively unhealthy in our diets in large concentrations. And instead, we need to be getting more omega-3 fatty acids from our diets. In general, corn oil has an omega-6 to omega-3 ratio of about 50 to 1, when ideally our diet should contain about a 2 to 1 ratio of omega-6 to omega-3 fatty acids. So corn oil probably is not is one of the least healthy oils for us to consume in terms of its omega-6 to omega-3 ratio. Olive oil, on the other hand, contains a fairly large amount of monounsaturated fatty acids in the form of oleic acid as the predominant fatty acid. And olive oil actually has a much better omega-6 to omega-3. It's about a 4 to 1 ratio of omega-6 to omega-3 fatty acids. Finally, safflower oil has been gaining popularity as a useful oil. It contains fairly large amounts of linoleic acid, a polyunsaturated fatty acid. In terms of its health factor, most linoleic acids are an omega-6 fatty acid, and thus it does kind of fall under the same problem that corn oil does, and can potentially have some somewhat damaging effects upon our health. Another form of fatty acid that was kind of brought to attention in the last 2 decades has been the trans fatty acid. And trans fatty acids normally do not occur very often in nature. You might find them from ruminant organisms that live in the guts of things like cows. But for the most part, most of the trans fatty acids that we see in our diet are synthetically derived. And basically, the difference between a trans fatty acid and a normally occurring fatty acid, if we look at, for example, oleic acid, and look at the carbon-carbon double bond here, and compare it to ellatic acid, with basically they're both 18-carbon fatty acids with a carbon-carbon double bond at carbon 9. The difference here is that the oleic acid has a cis double bond, the ellatic acid has a trans double bond. And while the oleic acid will not pack very nicely against the stearic acid here, ellatic acid would actually pack fairly nicely because that trans double bond is a whole lot more similar to a saturated fatty acid than it is to an unsaturated fatty acid. So basically, consuming large amounts of foods that contain trans fatty acids can ultimately be problematic. Now, there's been a big push to try to label the amount of trans fatty acids that are found in products, and of course, our people who tend to make foods that have a lot of trans fatty acids have pushed back against such regulations and have gotten around them by doing a couple of very tricky things. And one of them is to simply decrease the serving size. So whereas a serving size at one point might have been 2 cookies, if one cookie gets you under the 0.5 gram per serving limit for trans fatty acids, you can very easily just lower your serving size to 1 cookie. What that means is that the 1 cookie might only have 0.3 grams of trans fatty acids in them, but obviously when you go ahead and eat about 4 or 5 cookies, you're going to get a significant amount of trans fatty acids in your diet. There is really no safe level of trans fatty acids that has been established. My personal recommendation is to try to avoid them altogether. It used to be fairly easy to find products that had trans fatty acids in them. You simply looked for partially hydrogenated fatty acids, or I'm sorry, partially hydrogenated oil. And basically, the way that trans fatty acids come about is the partial hydrogenation process is meant to take polyunsaturated fatty acids and convert them into predominantly saturated fatty acids, but during the process you retain some of the unsaturated fatty acids. Well, the problem is that most of the fatty acids do actually react with a catalyst, but they don't get hydrogenated to the saturated fat, and thus when they go back to being an unsaturated fat, they go back in the most stable conformation, which is a trans double bond instead of a cis double bond. So that's the largest contributor to trans fatty acids in our diet. Other things to be careful for would be the interesterified fats that you find on labels now. Basically, that's simply a scrambling of the triacylglycerols after you go through the trans fatty acid forming process. It's simply another way to label things to try to get around the actual labeling of trans fatty acids, and also get away from the stigma associated with the partially hydrogenated fats. So most of our fats are found in the form of triacylglycerols, and triacylglycerols are esters of fatty acids that basically are 3 fatty acids attached to a glycerol molecule. So if we look at the structure here, here's our molecule of glycerol, and here are the fatty acids attached to that by an ester bond. Generally, we can break these down into this, since this is our predominant form of fat that we find in the diet. We can basically classify fats according to what kind of fatty acids are attached. So something that is considered a fat would generally be a solid at room temperature and contain predominantly saturated fatty acids, whereas something that were considered an oil would be a liquid at room temperature and contain a fairly large amount of unsaturated fatty acids. So, looking back at the table that I showed you on one of the previous slides of various oils, what you'll notice is that they contain a fairly large amount of unsaturated fatty acids. Usually they would have 2 or even 3 unsaturated fatty acids esterified to a glycerol molecule. In terms of the functions of triacylglycerol, the major thing that we use triacylglycerols for is simply energy storage. As animals, most of our energy is stored in the form of triacylglycerols. Whereas carbohydrate storage can maybe give us about a day worth of energy, triacylglycerols could give us several weeks to possibly even a month or 2 worth of energy. So the other things that triacylglycerols are used for is that some organisms use it for insulation. Marine mammals that have blubber, all that is simply a big layer of triacylglycerol that helps the animal maintain their body heat, and also it can be used on the surface of animals as a water repellent. So because of the hydrophobic nature of the molecule, it tends to repel water. We also use this in the, or at least used to use this in the production of soap. We now, of course, have much cheaper and much probably less healthy ways of obtaining soap. But basically, by hydrolyzing triacylglycerols by using sodium hydroxide, that was how we used to obtain the soap that we used to use. And some people do still make soap in that manner.